The natural logarithmic function, or the natural log function, is one that you've probably been introduced to in pre-calculus or maybe algebra or whenever. But there is a more formal definition than probably was given to you when studying in pre-calculus. So if we go back to the idea of the power rule for integrals, we know that if as long as the power is not -1, that x to a power is the way you take the antiderivative is you add 1 to the power and then divide by the new power, and then of course add your arbitrary constant. But the question becomes, what happens when the power is -1? What do we do? Well, it turns out that there is a way to represent this, but it's a special function. It's not what you think of as sort of a single polynomial function. It's this idea of a natural logarithmic function, or a natural log. And what we do is we take that power, so in this case this would be like t to the -1, and we write it as a definite integral from 1 to x. And what we find is, by the fundamental theorem of calculus, what this would be the antiderivative of whatever this function is evaluated at x minus the antiderivative evaluated at 1, right? That's the first fundamental theorem of calculus. But what we do is we construct a function that, when evaluated at 1, is actually 0. So that the function value at 1 is 0, which leaves us with the antiderivative only defined at x. So what we have here is a function that's defined in terms of the integral of a function. And I know that seems kind of odd, but what we find is that this is actually a pretty nice closed form. But the only issue is that for this particular one, even though if you look at this function 1 over t, 1 over, if it was 1 over x, for instance, that function has a domain of 0 to infinity, but also -infinity to 0. But the natural log does not. It can't evaluate numbers on the left side of 0. So you can't plug negative numbers into it. So it's only defined for positive numbers. And it's not defined for 0 either. And that's because if you look at this graph of f of t equals 1 over t, it has a discontinuity at 0. As t gets closer to 0, it shoots off to positive infinity because that number is really small. So 1 over a really small number is a really large number. And then as it goes to positive infinity, of course, it starts to tail out. However, it is important to note that this function here is positive everywhere. So what that's going to tell me is that since this starts at 1, if I evaluate at 1, well then that's from 1 to 1. We know that definite integral is always 0. But if it's from 1 to infinity, since the function is positive, that integral is a positive area. So as long as you evaluate numbers greater than 1, the natural log is positive. However, for numbers less than 1 but greater than 0, the integral would become negative, because even though this is positive, we're going backwards. So we end up with accumulating that sort of, you can think of as negative area or negative displacement. And so the natural log has that property that it's negative on the other side. And I'll come back to this in a second, but what you find is that this graph represents that concept pretty well. At 1, if you plug in 1 to the natural log, you get a 0. Anything you plug in after 1 is a positive value for the natural log. Anything from less than 1 to greater than 0, it's negative. And actually, not only is it negative, it goes specifically down to -infinity. And this one goes up to positive infinity. So what we have is our domain is all positive numbers, but our range is actually all real numbers. And this matters because that means that this function will pass that vertical line test, but it also covers the entire range. So we're going to talk when we get to inverse functions about how that's important here. It has no y-intercept because it's not defined at x equals 0, but it does have a single x-intercept. Notice that it's increasing the whole time. The function is always increasing over its entire domain, and that it's always concave down over its entire domain, which makes sense if you look at the definition. So by that second fundamental theorem of calculus, you remember that if you take the derivative of this function, then it's the derivative of this integral, but those have kind of that inverse operation, and it pops out, that it replaces this t with this x, basically. That's how that second fundamental theorem of calculus works. So if the derivative is 1 over x, because this is an antiderivative of 1 over t, then its derivative must be, 1 over x. Anyway, if it's 1 over x, well, if I plug in a positive number, this derivative is going to be positive. So that tells me on its entire domain you expect it to be increasing because the first derivative is positive. And if you look at the second derivative, well, that's just the derivative of this, so you get negative 1 over x squared. Well, no matter what you plug in, this is always negative. So therefore, it's always concave down. So these follow naturally from just an analysis of what the derivative of the natural log looks like. And we're going to be doing some examples and refreshing ourselves on the properties of logarithms, because using those properties are going to make dealing with derivatives and integrals involving logarithms way, way simpler.